For this exercise, we want to show that P and Q share an equivalent martingale measure. There's one measure that's in both of their sets of equivalent martingale measures, if and only if S1 divided by S0 at the terminal time, capital T, is a constant, almost surely, under P. Before we begin, it's just worth noticing that for any t in our time interval, y at time t is equal to xt divided by x1t, where x1 is the 1th element, not the first, because there's x0 as well, but the 1th element of the vector x. So now we're going to prove the equivalence. We'll first suppose that S1 at terminal time t over S0 t, which is equal to x1 at terminal time t, is some constant, p almost surely. That is, for p almost every little omega in capital Omega, this random variable is just equal to the constant c. Let's let p star be some element of curly p, that is an equivalent martingale measure for p, or equivalent to p, equivalent martingale measure for x. And we shall let E star then denote expectation with respect to this P star as normal. Since P star is equivalent to P, it holds that P star, the probability that x1t is equal to c, is also equal to 1. x1t is also constant, equal to the same constant as it is under P. And therefore, the conditional expectation under P star of the terminal value of y, given the information up to time little t, that is given the sigma algebra, curly ft, is equal to 1 over c times the expectation of x capital T, given ft. That's using this expression of yt that we had in the first moment. X is a martingale under this measure, so this is of course just equal to 1 over c xt. And again, using the expression of y that we had at the start, that's equal to yt. Just dividing by the terminal value of x1t. Well, actually, not quite. I've skipped a step here. Let me just make that explicit. So yt is equal to xt over x1t at little t, right? We've assumed that this guy is constant at terminal time, capital T, but not a priori that it's constant at all times little t. All we need to do is notice that, well, starting with one time step back, and then we can follow this reasoning inductively, that expectation of under P star of x1 at time terminal t, and x is a martingale under P star, so all of its component parts are also one-dimensional martingales. So this actually, I want to have, can use actually just t will work fine directly. So this is, of course, just constant. Right? This guy is under p star is constant almost surely. So conditioning, although it's, as we've seen, it's a projection down, it won't change almost sure events, because we are just looking at a smaller subset of omegas, but not probability 0 events. And that's equal to x1t. So actually x1 is a constant at all times because of the assumption that we have an equivalent martingale measure. So this is now proving this equality, that yt is actually equal to xt divided by c at all times little t as well. So that has proven that y is a martingale under p star, and therefore that p star, since it's equivalent to p, is an equivalent martingale measure for y. Now, all of what we've done has been for a general p star in curly p, the set of equivalent martingale measures for x. And so the final thing we need to note is that p star, at least one p star does exist, because the market is assumed to be arbitrage free. So x, the discounted price process, has an equivalent martingale measure. That's the first fundamental theorem of asset pricing. So there is at least some p star that exists. So so that p star is also an element of Q, and their intersection is non-empty. Now we're going to suppose the opposite direction. Curly P intersect curly Q, that impossible letter to draw. So suppose it's not equal to 0. Let's let again P star be, that's an L, not a Q, an element of the intersection of these two. So an equivalent martingale measure for both x and y. Then, first thing to note, the process is x1 and y0 equals 1 over x1 are martingales under P star. That's what we already used above, that the component processes are martingales if the entire d-dimensional process is a martingale. Thus, the expectation 1 over x1 at terminal time t, given f0, the trivial sigma algebra, is of course from the martingale property 1 over x1 naught equals, again using the martingale property, 1 over the expectation x1t given f0. Since the map x to 1 over x for positive x is strictly convex, and that strictly is crucial, Jensen's inequality for strictly convex functions tells us that the expectation of 1 over x1t conditional on f0 is strictly less than 1 over the expectation x1t f0 if and only if 1 over x1t is not almost surely constant. This is a feature of Jensen's strict inequality for strictly convex functions, which doesn't appear in his inequality for just convex functions, and that's why we require strict convexity here. Well, we have, of course, that these two expectations are in fact equal. That's what we just proved using the fact that both 1 over x1t and x1t are martingales under P star. So thus we have from above the contrapositive of the left-hand side and therefore of the right-hand side, 1 over x1t is P star almost surely constant. Since that's true, then of course x1t itself is also P star almost surely constant, and by equivalence P star and thus P almost surely constant, because P star and P have the same almost sure events. That's what equivalence is, right? If an event is probability 1 for one, then it has probability 1 for the other. I haven't written the word constant there, very well. Constant. And that's what we had to prove. That's both directions.